I'd like to thank the organizers for the opportunity to speak. The title of this talk is Nasal Sprays, New Insights and Discoveries. It's a pleasure to be part of SCONA 2022. I'm Worth Longest, and I'm presenting this work in collaboration with Arun Kalonjiil. Arun is a postdoc in my lab and performed most of the CFD that I'll show today. This effort is part of a larger project sponsored by the US FDA. Our program officer is Ras Walinga, and Lala Golshahi is the PI of the project. Our part of the project was to develop a CFD model for determining bioequivalence of nasal sprays. And our first step was to validate CFD predictions of nasal spray deposition in vitro nasal airway models for 2 spray pumps. Based on our experience with CFD and with nasal sprays, we thought this would be a relatively easy task. We proposed laminar and turbulent flow solutions, high initial droplet velocities to start from in vitro measurements, one-way coupling between the phases, assuming the standard droplets deposit on touch boundary conditions, things that we had done before. Whenever we went to compare with the in vitro data from Lala's lab, we were very surprised at how poor the agreement was between the initial CFD model and the in vitro predictions of anterior and posterior deposition for the 2 really common nasal spray products that we saw. So we were in the range of 50% relative differences from the in vitro data. And that really caused us to dig in and ask what transport phenomena might we be missing. Areas that we looked at before included 2-way coupling, and we asked the question, do high spray momentum and high droplet volume fractions near the spray nozzle tip combine to create a cloud motion effect that could enhance nasal spray deposition in the nose? And the more we thought about this, the more we realized, yes, it probably does. And also liquid film motion. Does the initial splashing and spreading of the nasal spray in the anterior nasal wall cause a change from the initial droplet on touch assumption? And does liquid film motion occur after the spray is initially delivered? And this was something that we saw with the experiments. So when we started this, we saw big differences between our initial assumptions and what we were seeing in the lab. If we go into a brief history of cloud motion, cloud motion as it relates to aerosols is a phenomenon in which the particles in mass behave differently compared to the individual particles. They behave collectively with a higher momentum. We know from classic texts that cloud settling can occur. Fuchs wrote on this, as did Hines in his aerosol science book. When it comes to cigarette smoke and its high concentration, Martonen proposed that the high concentration of these nanometer, say 200 to 400 nanometer particles, cause smoke to deposit as a much larger size aerosol. Brody and Robinson proved this out some analytically. And when we previously looked at the Respimat oral inhaler, we included some cloud motion effects to capture the extent that that aerosol reaches when you just actuate the device. So when you push the button on the Respimat, you get this beautiful billowing cloud extending out from the inhaler, much further than the small particles would do otherwise. And in a previous CFD paper, we showed that that was 2-way coupling, cloud motion effects, and we had to include that phenomena to get the right deposition and match the extent that the plume extended with in vitro experiments. We were then surprised that we hadn't previously explored the importance of cloud motion with nasal sprays, where the droplets are larger and the momentum's higher. When it comes to liquid films and respiratory drug delivery, here we're referring to both when the spray interacts with a surface, we get droplet formation, rebound, re-aerosolization, and we also get a momentum effect of the liquid film that's on the wall. So all of this can be important. There are submodels here that have been developed in the combustion literature and been around for some time. That spray wall interaction is different than liquid surface motion, which can also come into play whenever we have these high mass liquids depositing on the surfaces. And it's even more complex in the nose, where we have the high mass liquid depositing on already present airway surface liquid. So we saw the need for a spray wall interaction model and a enhanced liquid surface model after deposition. As we were developing this, Jin-Sheng Shi, who's talking later today, published a nice paper with his group on using this post-deposition liquid motion to target the olfactory region for nasal sprays delivered in a head-down position. So we were, in a sense, working in very similar area, very similar topic. The nasal airway model and spray pumps of interest. We're looking at the GSK Flonase spray pump delivering fluticasone with a fairly high volumetric median diameter of 120 micrometers. The Flonase Sensimist we think of as the gentler product, the smaller diameter, and the lower shot weight. We considered a couple of adult nasal models in this work. In some of the simulations that I'll show, this was a model with average volume to surface area, our subject 16 adult nasal airway model. And then an outcome of this FDA contract was we also selected a different representative media model that was used in some of the simulations. We used similar actuation conditions between the models and the experiment. And an important, we might call it innovation or change that we did in this work was we included a spray adapter ring in the in vitro nasal model that didn't block the airflow passage substantially, but gave us good alignment of the spray nozzle tip between the CFD and the in vitro experiments, because we saw just millimeter changes in how the spray tip was aligned would cause big changes in anterior-posterior deposition. This shows some measurements from Lale's lab comparing the Flonase and Flonase Sensimist. The key is that with the Flonase, we're delivering about twice the liquid volume and shot weight compared to the Flonase Sensimist, and I already mentioned the larger particles with the Flonase. Surprisingly, we get similar velocities, and with the Flonase, we have a longer spray duration. So we started out looking at the importance of cloud motion. And just as a review, when we look at, in aerosol science, the effect of the gas field on the droplets, we call that one-way coupling. When we then also include the collective effect of the droplets on the gas field, we call that two-way coupling, which I'll use synonymously with cloud motion. Einstein found cloud motion fascinating. He also found it difficult, but of course he didn't have the benefit of CFD. With CFD, we can, not easily, but we're able to include this two-way coupling in our simulations using an iterative style process. We started looking at the potential two-way coupling in nasal sprays, first experimentally. Here we have a captured image of Flonase actuating Flonase Sensimist. We set up a computational geometry that went out through 32 centimeters to capture the plume extent, as is done in vitro experiments. But then we put our nasal model on top of the computational geometry and realized, wow, that there's a lot of dense flow occurring in this first centimeter or two where the anterior nose is located and where we're trying to match this very close boundary between the anterior and posterior deposition fraction for both Flonase and Flonase Sensimist. So while a lot of the work that I'll show includes this entire computational geometry, remember that most things are happening and are important very close to the spray nozzle tip. This slide shows an image of the Flonase actuating into the geometry, and again, we really get this almost water squirter effect. So it's surprising that we've gotten by with aerosols for so long, capturing in vitro deposition. If we look at the animations of the two-way coupled full simulation, we see the droplets progressing, and I'll strip away the larger size droplets here in a minute so we can really see the cloud motion that's occurring. But what I want to show on this slide is the air velocity. So here, this is the air velocity that's occurring from the two-way coupling, and you'll notice we're up to around 15 meters a second air velocity occurring very close to the spray nozzle tip. Now, a trick that we'd use with the Respimat was to send in a mock air velocity to capture this effect of the particles. What we found when we tried to do this with the spray pump is that it didn't work. We saw a very different velocity profile, and it didn't really enable us to match the in vitro data. So here we see similar results for the Flonase Sensimist. We see the plume of spray progressing into the geometry. In this animation, again, we're seeing for the Flonase Sensimist, even though it's a smaller aerosol, we see high velocity droplets inducing a high velocity flow inside the geometry, especially very close to the spray nozzle tip. So we felt like it was critical to include this CFD simulations in some way. This slide compares for Flonase Sensimist, two-way coupling in the left panel, one-way coupling in the right panel. And we've stripped out the droplets larger than 50 micrometers, remembering that for Flonase Sensimist, around 50 micrometers is the volumetric median diameter. So what you see represents half the flow mass. We see that the two-way coupling extends much further into the nasal geometry over the first 30 milliseconds. So the one-way coupling in the right panel doesn't go very far at all in the first 30 milliseconds. The two-way coupling really has a large momentum effect, and we see this beautiful cloud plume of the smaller droplets evolve through the flow field. So this cloud effect pushes the smaller droplets further into the geometry, and this has an effect on deposition. So to sum up some takeaway messages, the idea is that whenever we strip out the larger droplets, we're really able to see this cloud motion effect in the smaller half of the particle size distribution. For one-way coupled simulations, we see a minor extent of the plume into the nasal geometry, but when we include the cloud effect, we can push the nasal spray almost all the way through the nasal geometry, a much further extent of the aerosol. We then started looking at ways that we could include two-way coupling. For Flonase, we have an actuation period of around 100 milliseconds. For Flonase Sensimist, the actuation period is shorter. We ran fully two-way coupled simulations through these actuation periods. And what we realized was that we get evolution to a quasi-steady state of two-way coupled flow in around the first 10 milliseconds. So what we were able to do was to run the full two-way coupled through the first 10 milliseconds. During that time period, we see significant formation of these air velocities just coming from the two-way coupling within the nasal model. This is for Flonase. Through this first 10 milliseconds, then we don't get much further evolution through the additional time. This would be out through for the first 20 milliseconds. The streamline profiles are also quite pronounced based on just the two-way coupling. Quantitatively, we showed that the volume average velocity levels out after the first 10 milliseconds or so. And so this was our time point for setting up the flow field using fully two-way coupling, and then we'd freeze that in time, forming a quasi two-way coupled approach. After that first 10 milliseconds with that frozen flow field, we would inject the spray particles and simulate how they behaved. And using this two-way coupled approach that Arun devised, we were able to reduce the runtime by around an order of magnitude and still achieve good agreement. This is our comparison with Flonase Sensimist in vitro data. The in vitro data is from Dr. Golshahi's lab, and it's captured in the table that you see here at the bottom. The in vitro data is on this lowest row. If we focus first on deposition in the posterior or back portion of the nose, our target was 7.7% of the delivered spray mass. With the one-way coupling, we under-predicted this. The spray wasn't pushed far enough, so we had more deposition in the anterior part of the nose. With the two-way coupling, we much better captured this higher in vitro fraction in the back, in the posterior part of the nose. So with one-way coupling, we were around a 47% relative error. That was reduced to below 10% relative error with the two-way coupling, and our relative error in the anterior part, as well as the drip that happened experimentally, went from around 4% to under 1%, including the two-way coupling for the Flonase Sensimist. When we went to Flonase, again, we have the in vitro deposition on the lowest row. The in vitro Flonase deposition in the posterior part of the nose was 9.3%. When we simulated this with one-way coupling in CFD, we under-predicted it as expected, but surprisingly, whenever we went to two-way coupling, we over-predicted it by about the same amount. So we started with a 30% under-prediction with the one-way coupling, and we went to a 30% over-prediction with the two-way coupling. In terms of the anterior components here, the relative errors were within 5% both ways. So no big loss there. What we decided was that two-way coupling is important. It's having an effect. We can't just rule it out for Flonase because we saw a big effect here. We saw a big swing going from 6 to 12%. But perhaps there's more going on. And this led us into evaluating more the effect of the liquid film formation. Before I show that, I'll quickly show results where we also included an inhalation velocity. So we started the sprays at the beginning of a sniff profile, and we saw a similar result for both Flonase Sensimist and Flonase, that whenever we included the two-way coupling, our posterior relative errors went down. For Flonase Sensimist, anterior was acceptable. And in the case of the Flonase, our one-way error of around 60% went down to around 30%. And so, again, we're seeing the two-way coupling have an impact even when we have flow. However, we need to do more work whenever we're dealing with the Flonase as opposed to the Flonase Sensimist. So this was where our spray droplet wall interaction and post-deposition liquid motion model came into play. So as I described, we're looking at the spray wall interaction components where the spray interacts with the wall. We get the splashing and spreading, and then we can get subsequent post-deposition liquid motion. We're keeping these abbreviations separate for now to indicate that it's a lot of effort to do both models. I'm sure we could condense these into a shorter abbreviation, but we'll leave them separate for now. And so the aim is to simulate the nasal wall interaction and accompanying surface liquid layer dynamics for Flonase and Flonase Sensimist. In this case, we were able to use our medium adult nasal model. You see here the anterior part of the nose, and we also broke up the posterior part of the nose into subregions for some of these results. So switching over to the pointer to play the animation. So this is for Flonase. We had 2 spray cycles, so 2 sprays, 2 seconds apart. And you see the first spray hit. This is a contour of thickness of the spray. And notice how it then flows from the posterior part of the nose to the anterior part. Now we have the second spray occurring. And again, we get this flow. So in the model, we've got the spray dynamics going on. We've got the post-deposition liquid motion going on. And we're accounting for the formulation viscosity, which was shear thinning, but also depended on time, so it was thixotropic. Formulation surface tension, and also wall adhesion to the in vitro model. This is the model for Flonase over time. And again, you see as we progress, the second spray occurred at around 2 seconds. We get this flow of the liquid from the posterior part of the model into the anterior part of the model, which influences the final resting place, obviously, and the agreement with the in vitro data. For Flonase Sensimist, fortunately, things stayed put. There was less mass, less volume, and therefore we got less flow into the anterior part. So this slide shows our comparison with the in vitro data shown in the middle. When we started with the two-way coupling in the blue bars, we were a good bit off for Flonase. Whenever we then went to the spray wall plus liquid motion, we were able to capture the part of the posterior drug mass that then went into the anterior bit of the nose and gave us much better agreement with the anterior in vitro deposition fraction and the posterior deposition fraction. When we then further subdivide the posterior part of the nose into subregions, we're still more accurate with the spray wall liquid motion. Here, relative differences are a little higher than we'd like, and we're still working on that part of the model. So in conclusion, to bring this back full story, we started with a little false confidence that simulating in vitro deposition in a nasal model would be straightforward for 2 spray products. We found that whenever we went with our standard models, we had relative differences of 30 to 50%. When we included two-way coupling, We improved anterior-posterior relative differences to within 10% for Flonase Sensimist, but we were surprised we still weren't done. We still had this big disagreement for Flonase. We had to include the two-way coupling, the surface wall interaction, and the post-deposition liquid motion models to improve the anterior-posterior relative errors to within 10% for Flonase. Unfortunately, this didn't harm our agreement for Flonase Sensimist. So the take-home messages that I'd like to leave you with are: number one, two-way coupling should likely be included or approximated for current nasal spray products. Now, there may be other ways to do the approximations. We like the quasi-two-way steady coupling model that Arun developed. It didn't work to use the airjet approach that we previously used for the Respimat, but there may be other approaches out there that could work. Our second finding is the need for surface wall interaction and post-deposition liquid motion models in some cases. It may not always be the case for Flonase. If we just done one pump or one spray with a Flonase, we may not have needed to include these. But it's complex, so it depends on the spray formulation, the shot weight, the number of shots, the nasal geometry, and positioning of the spray nozzle within the nose, and the point of initial spray wall contact. So all of this comes together to determine if we need this surface wall interaction model. So this created challenges for matching in vitro and in vivo data with CFD, but it also creates opportunities for targeted drug delivery. So I think Jen Chung's going to touch on this, and it also leads to an article that we'd like to do that we could call the big sniff. So if we inhale hard enough, we can likely show that a lot of what we deliver as a nasal product can be moved from the anterior to the posterior part of the nose, but then where in the posterior nose becomes a big question. So I'll quickly just show some of the supporting publications that we have that went into this work. And I'd like to gratefully acknowledge funding from the US FDA for this work and our PO, Ross Wallinga.